part of our exploration of memory, we're going to delve into notions of scope, of linkage, of related aspects to that, to look at how the data that we create is visible and to what parts of the program is visible to. So by storage duration scope, it's worthwhile pointing out that in C++, in terms of how the language has evolved, this is a little bit messy, and you'll probably see that. And we'll come back to sort of reflect on that a little bit towards the end about how it is done in traditional C++ and maybe how more modern languages have improved upon it. But we'll start off considering the notions of duration and scope, how long a particular piece of data lives and how widely visible that piece of data is. And if you can recall back to the last talk where we looked at memory, we finished off on a slide that looked at how our program is set out within memory. And we identified there's a region set aside for static storage, for holding variables that always exist. We will then have our heap for storing dynamically allocated data, things we bring into existence using the new keyword. And we'll have some automatic storage on the stack for things like parameters and sort of local temporary variables that are created. And these three different stores, if you like, tie in. We need three different ones because data exists for differing periods of time and has to have different levels of visibility. So there isn't an optimal one-size-fits-all here, but if we use different stores, different approaches, then we can store we can tie in the type of data to the particular store to make sure it works fast and efficiently. We'll look at each of them here. To do this, we're going to be thinking about notions of scope and of linkage, and both of these are somewhat similar. Linkage is a little bit more C++ oriented here, and you'd be right in terms of thinking about the process of compilation going into the process then of linking at the end. Scope is, if you declare a piece of data, scope is how visible that piece of data is. Is it visible within just the method in which it was created? Is it visible outside of that? So it ties into how broadly visible the data is. Think about global scope, then this is something that's going to be broadly visible. Now in C++, a few things we want to bear in mind. So if we look at scope, defines the variable's visibility should be within the compiled file. So global scope known throughout the file after the point of definition. So this is a characteristic of C++ that if you declare a global variable, it is only visible notionally to lines of code underneath it, not anything above it. And that isn't true, for example, of other languages like Java, for example. And this ties into the long-standing history of C++ that 30, 40 years ago, in terms of a compilation process, you would start at the top of the program and you would work your way down compiling it as you went. So something had to be declared, defined before you were then able to use it. Nowadays, you can easily have multi-pass compilers that can go zoom down through, work out everything that is there, build up different tables of this and of that. So it's not a restriction you have nowadays, and it would be an unnecessary restriction nowadays, but it's for legacy reasons something that C++ has. Local scope is only known within the defining block of code, again after the point of declaration where we define it. Linkage then, now the key thing here, linkage defines how a name can be shared across different units, compiled files. In C++, each CPP file is compiled separately, independently, on its own, as a standalone entity. You compile one, you compile another, you compile another. After all of these entities have been compiled, they're then linked together, stuck together at the end into a complete whole. So again, that makes sense for reasons of resourcing and for various other reasons as well. So for some of the data that we create in C++, we'll only be interested in having scope within its own local file. Some other data we might want to say, well, I want other CPP files to have access to this. That's where we want to give it linkage outside of the CPP file that we define it, that is defined within. And we'll see how we can manage this. But again, key thing to note, these are traits or characteristics of how C++ has evolved and changed over time. And quite a lot of these things will be better hidden to the ROM, were better managed, more elegantly expressed within modern programming languages. And C++11 actually recommends you do a different approach, but we're looking at old style here. So just to go through these three, we'll start off with automatic variables. So function parameters, ordinary variables defined inside the function use automatic storage. The name automatic comes because they're automatically created on the stack, and they're automatically discarded whenever they go out of scope. They're not visible anymore. You can see a small fragment of code where we have a method foo with an int a. So a is an automatic variable. It's a, it exists. It's going to be created on the stack. We'll be able to use it inside the body of the method. It has scope within the foo method. At line 3, we're creating another int called b. It too is an automatic variable, automatically created, stores on exists on the stack. We can assign it the values we're doing here. We can use it. And at line 4, whenever we leave that block of code, both a and b get to be automatically discarded from the stack. They're not used anymore. So automatic variables, local variables, whatever you want to call them. So a little bit more elaboration to it here. They're not really too much. So automatic variables are allocated whenever execution enters the block. So whenever you enter in a new block of code, and it's the same notion of a block of code when we looked at the process of optimization, sort of a flow through it. So each block of code will know, or through the compilation process, it will define which variables, automatic variables we need to create within that, and they get to be automatically allocated on the stack. However, they don't come into scope until the point at which they are actually defined, or the point of declaration. So we have our foo method has int aval, so aval will be created. At line 3, just as we enter into that block of code, we now have aval as in scope. We can access it, we can write to it, read from it, things like that. Line 4 to line 8, we have another block of code. So whenever we enter into it, we know, or we've worked out within that block of code, we have one other automatic variable, bval. It'll be allocated on the stack. And at line 6, whenever we have declared the bval actually exists, that's when it becomes into scope. That's where we can access it and modify it. Line 8, bval gets to be discarded, is out of scope. And line 10, aval gets to be discarded, again, is out of scope. So these things all happen automatically as our program is executed. Because that happens automatically, because we would routinely do this anytime we call a method or function, we're going to have to maybe create a number of these anytime we create a couple of local variables for a counter or whatever, we're going to have to do this. We need to have a fast, efficient means of bringing them into existence quickly and discarding them quickly. And it turns out that in terms of the normal flow of execution, a stack structure offers a very good fit here. So the stack is called a stack in terms of how it manages that memory because it is a stack. That's the type of structure that it uses. So anytime we want to create a new automatic variable or variables, we simply go to the stack and we say, okay, it's an int. I'm going to take the top 4 bytes of memory after the stack. I'm going to assign them to this particular int value, and I'm going to increase the stack pointer by 4. So notionally, we push an int's worth of data onto the top of the stack. If we have to get another int automatic variable, we push that onto the stack as well, again updating our pointer. So we're preserving memory as we go through, and we can then use that memory. Whenever we come to the end of the block of code, we'll know how many variables and of what type we need to discard. So again, all we're doing then is we're resetting the stack pointer back to where it was before we entered into that block or before we called that particular method. Now, it is only changing the pointer. We don't care about whatever data we wrote there. It's just still going to sit there. Effectively, if we allocate something again, we'll reuse, we'll write over it in terms of the new processing that we're doing. So stack manipulation, we're not interested in cleaning things up. If we have an automatic variable, it's up to us to assign it initial value. We're simply interested in being able to quickly allocate, to jump forward or jump back by way of reserving or deallocating space in memory. So a stack type structure works perfectly for this. Lovely, fast and efficient. They'll aside that there is register values where there's register keyword. It's appreciate it in C++11, don't really use it anymore. Where in some cases, if you feel that other than storing a variable in memory, you really want to store it as one of the CPU registers, you could express a preference to the compiler that should happen. C++11 is now basically up to the compiler. It'll know the architecture that it's running on and what's available to it, and it'll decide which, if any, of the variables will get to be stored as part of the register set of variables. So static variables, this is where it gets a little bit more complicated. So static variables, they exist for the complete duration of the execution of the program. So this is the block of memory right next to the machine instructions, which always exists, always contains our static variables. Now, if it's static, it means it always exists. It doesn't necessarily mean it's always visible or is visible everywhere. It's just that this piece of data always exists. That's the key definition of static, always there. The notion of scope is separate to this. And this then ties into the bit at the bottom. So if we're thinking about variables that always exist, they may have different types of scope. Over on the right-hand side, first of all, no linkage. So in this sense, it's the same as an automatic variable. It's only visible, it's only in scope inside its one block of code, but the thing always exists. So anytime we come around to that block, it'll be there again, waiting for us. We could have internal linkage, where we're saying that it's visible just within this one compiled file. Or we could have external linkage, where we're saying that this is a variable that is visible everywhere within the program. So if I have a program that comprises 10 CPP files, I want this one variable that I'm declaring to be accessible, visible, potentially within all of the other CPP files, anywhere at all. So this is the notion of static variables, and we'll look at how we can deal with the scoping issues in the next few slides. A little bit at the bottom about how you can initialize these in terms of giving them a default value. If we're thinking about probably the most visible one, these would be global variables. So external variables, also known as global variables, are defined outside of any function. That's how you create one in C++. So a little fragment of code. At line 1, we've got int some global is equal to 3. So int any name you want. And at line 3 and 4 down here, we've got our main and some execution. So we're declaring something outside of any block of code, outside of any method, outside of any function. In C++, that is automatically then considered to be a global variable, something with external visibility, is static, always exists. So that's how you create in C++ a global variable. Having declared it in line 1, in this case it is at the top, we can access it within that CPP file any point beneath the point of definition. So I have static storage duration and have external scope. That's what we mean by global. Now, I'm going to talk about the one definition rule, and then we'll talk about why we actually need it. So in C++, there is a rule, the one definition rule, which states there can be one and only one definition of a variable. So if I want to define a variable, to say that it exists, it is called this, it is of this type, and it has this particular value, or I want to reserve some memory for it, I can only do that once. And this gets into the distinction between defining something and declaring something. So if I declare it, I can say it exists, whereas making the notion that it's somewhere else that it exists, but I'm just highlighting the fact that it exists. If I define it, I bring it into existence. So that's the key point. I'm only allowed to bring a variable into existence once and only once. Now, why do we need this rule? We need this rule for a couple of reasons. Let's assume I have two C++ files. In one C++ file, I'm defining a global variable that I want to use both in that C++ file and in the other C++ file. So I can declare it, as we saw on the other slide, quite easily in one of the files. I've defined it. It exists within that particular file. In the other file, it is compiled separately. So it's compiled completely independently of the first one. But I've got to have some way of indicating that I'm compiling this second file. I want to use a global variable, let's say called A, but it's not actually defined within this file. It's defined somewhere else. So I'm saying, at this case, I'm basically declaring that it exists. I'm saying you will find this somewhere else. It isn't defined here, but it is defined elsewhere. And I need a means of doing this, and it's going to be using the extern keyword. And if I do that, effectively it says, okay, the compiler will then proceed under the assumption that, right, okay, there is a global variable called A defined somewhere else, and you're going to use it. Brilliant. Whenever you get to the process of linking, of trying to link these different things together, that's where those assumptions then are tested. So if you're linking this that says there is a global variable called A, at the point of linkage, you will try to find, well, where is it? What file contains it? That's the one I'm going to link this code into. So we need to have this because in C++, each file's compiled individually, separately, so that if we want to access things, we need to have one means of saying it exists, but I'm not bringing it into existence at this particular point. The extern is the keyword that C++ uses to do that. It's known as a referencing declaration. So I can declare that it exists, but I'm referencing the existence of it being somewhere else. No new storage is located. Slightly confusing, but that's just part and parcel of the requirements of this. So you can see an example of it here. Let's say on lib01, I have at lines 2, 3, and 4, I'm creating 3 global variables. So line 2, int a, just an ordinary declaration, because it's not in a method or function, it automatically becomes static external scope, global variable. Same with line 3. In this sense, we are not only defining it, we're initializing it as well. And in line 4, I'm using the extern c equal to 3. Now that is also creating a global variable. I'm using the extern keyword, but because I'm assigning it a value, that is instantiation of it. Now I put it in because that is a valid definition of a global variable. You should not do that. It is confusing. Using the extern keyword, only use it when you actually are referring to something that is defined elsewhere. Now, let's assume lib01, we declare these 2 global variables. It'll be compiled quite happily. We then go and compile a separate file, file01 and file02. If I want to make use of those global variables, to access them, to manipulate them, to do things with them, I need to have some way of saying them and making them visible to say that they exist, to declare that they exist within file01, but to indicate that they are defined elsewhere. That's where extern comes in. So at line 2, extern int a, basically it says there's a global variable defined somewhere else called a, it's of type int, and assume that that exists. And it will. And when it comes to linking, it'll then test to see, well, does that actually exist? And if it couldn't find a variable called a, then you'd have a linking error being generated at that point. And ditto with file02. You can get problematic situations coming out of this. Now, the problem with this is that the default way of creating a global variable is, and you see a couple of examples in here. So file01, I do int var is equal to 100, and I create this as a global variable, external linkage. Now, let's say I write file01 and you write file02. So you come along to file02 and you too create a global variable called var is equal to 100. So when you're writing that, you thought, yeah, I want a global variable, I'm going to call it var, I'm going to give it whatever value, it doesn't really matter. At the minute we have broken our one definition rule, these things will not link together because file01 declares a global called var and file02 declares a global called var. And you have a conflict. File03, should it exist, doesn't know which of the 2 vars are the ones that are going to be used. So we can't get around this. This would be a problem. So in C++, you need to have another mechanism to say that, yes, I want to create a global variable, but in terms of the scope, I don't want it to be external to this file. I only want it to be global within this one file that I'm compiling. So it has internal linkage, not external linkage. And the way to do that in C++ is to use another keyword known as the static keyword. So you can see down in line 2 in file02 at the bottom, we're doing static int var is equal to 100. Now, that's fine. That will be defined okay. It won't cause any naming conflicts. Effectively, what we're saying there is that we have a global variable which has a scope just within file02, and the static keyword indicates that. And notionally, it hides, it replaces the global variable called var defined in file 01. So that if in line 4 down at the very, very bottom, we do int a is equal to var, we're using our own static local global variable to hide the external global variable. Again, that's just part and parcel of how do you differentiate between these different scopes. Finally, you can also use static for automatic variables as well, or not automatic variables defined within a block of code in the same way you'd normally have them there. So if you declare that to be the case, they are static, they always exist, they only have scope within that particular method call, which means that from one call of that method to another, you'll always retain the variable. It's not lost, it's not discarded. It's a bit of a niche feature in terms of being able to recall these things. If you wanted to, for example, to count the number of times a method was being called, for example, you put in some debugging code, there you might do that. So it's always a static counter that simply increments the number of times you would call the method. Niche has its uses, though not too many of them. Right, so having gone through all of this, you might think that the different forms of linkage are a tad confusing, needlessly messy in C++. In my opinion, you'd be right. If you look at how modern languages that have replaced C++ have built upon it, how they have handled notions of scope, of access, of duration, there are cleaner, more consistent, better ways of doing it, and those languages do draw upon them. C++'s defense in C++, well, not even 1198 and so on, they basically recommend not to bother using these things. It's a bit of a messy throwback. To use namespaces, which is similar to how modern languages handle scope and duration access as well. So it's a throwback to olden times. But it's worthwhile highlighting this simply to get across that languages do evolve and change over time. And there is this process and evolution of how we approach programming. And some language features, particularly if you find yourself dealing with C and C++, they can have historical reasons why they were created, but sometimes those historical reasons don't translate into the current day. A few other things just to finish off. I'll mention briefly here about creating memory on the heap. So this is where we're using the new keyword to allocate a chunk of memory. And when we're finished with it, using the delete keyword to free up that chunk of memory. So if we wanted to create a new object or an array or an int, doesn't matter what it is, and I'm anticipating that it'll live for a good period of time, that's when I would create it on the heap. There's a whole range of different types of algorithms you can use that work out, well, where can I find a free chunk of memory? Can I slot it in here? If I'm deleting something and it's producing a fragmented chunk of my memory within the heap, how can I manage that, move things across? A whole lot of processing that can be involved with memory management so that we manage the heap, we look after it, doesn't become too fragmented, that if we want to allocate a big chunk of memory, we can find it, and things like that. So it's interesting to delve into. You may have been interested in doing that. Key takeaway at this point is that it's more expensive to allocate memory on the heap. There's a cost associated with allocating and deallocating. So we need to be mindful that that cost has to be paid when we are making use of the heap. But we'll come back to that when we're looking at creating objects. Well, one little bit here. I suppose C++ is infamous, I suppose, in terms of things like memory leaks. Java, C# they are managed languages, which means that the process of allocating and deallocating objects are managed for us, the programmer. So it's much more difficult to have a memory leak in say, Java. The example of the piece of code here is probably quite telling. So we've got a method called foo. We've got the use of the new keyword. So there it's going to create a new array of integers. 10 of them in total, so assuming 4 bytes, that's 40 bytes of memory that will be allocated, reserved on the heap for storing that array. We're calling it data and we're getting back an integer pointer. So there we've got a pointer to the chunk of memory that was reserved for us on the array for storing our 10 integers. And we then use that in some way or some form. If we get down to line 5 and we haven't used the delete keyword to say that we have finished with that chunk of memory, we don't need it anymore, then we will exit out of that block. Data will get to be deleted. That's just the pointer, not the actual memory itself. So we will forget about the location at which we pointed to it. But inside the memory tables, we will still have allocated and reserved that chunk of memory. So that represents a case where we've allocated 40 bytes on the heap, which we'll never ever get back. It's always going to be reserved. And if we were to repeatedly call through, we would allocate another 40 and another 40 and another 40, and eventually the heap is going to encroach up and clash with the stack, and we'll run out of memory. That's a memory leak. So it is important, vitally important in C++ when we're making use of the heap, always to remember to pair a new with an appropriate delete whenever we can safely discard of that memory. Key takeaways in this, a couple of them here. So understanding how your data is stored and managed in memory is key to writing efficient programs. It is. We want to have a clear understanding of how we're going to be setting out and storing and structuring our data actually within memory. C++, we can go down to a fairly low level in terms of thinking about the heap, in terms of thinking about the stack, and we will, as we go through, want to relate this into higher level languages as well. The notions of scope and linkage are important. They're a little bit messy for historical reasons in terms of how they're handled in C++, but it's useful thinking about any language. Well, how does it do this? And do you like the way in which it handles scope, linkage, duration, those types of things? And particularly when we get into dynamic memory allocation, this is where I'm going to be drawing upon a lot of these different notions and concepts, but we'll get onto that and you'll see that's the case.